In this part of the video, we're going to talk about applications of limits to rates of change. In the first part, we introduced the concept of limit and we gave you a tool on how to calculate limits using a table of values. Now, what we're going to do is we're going to use that method to calculate limits to show you how to calculate instantaneous rates of change. For that, let's introduce first what the concept of rate of change is. A rate of change is a measure of how a function is going to change over a given interval. Usually the examples that we're going to be working with relate to kinematics. So we're going to use concepts such as velocity and acceleration to describe rates of change. There are two types of rates of change. The first type is an average rate of change. An average rate of change or an average speed can be calculated by taking the distance traveled, so we're going to call that delta distance, over the time it took to cover that distance. For example, if you were to cover 8 kilometers in 2 seconds, then your average rate of change would be 4 kilometers per second. Let's take our first example. Find the average rate of change for a particle whose distance is given by the function 3x plus 2 over the first 4 seconds of motion. The first thing we need to know is where was the particle in the beginning, so at x equals to 0, and where was the particle at the end after 4 seconds, so x equals 4. We're going to evaluate f of 0 is going to be 3 times 0 plus 2, so that is equal to 2, and f of 4 is 3 times 4 plus 2, that is equal to 14. Now we want to know the average rate of change for this particle. So the average rate of change is going to be 14 minus 2 divided by 4 minus 0. Now 14 minus 2 is 12, 4 minus 0 is 4, and this is equal to 3. The average rate of change is 3. Now look at this. The average rate of change that we found is 3, and the slope of this linear function is also 3. For a linear function, the rate of change is given by the slope of the line. Now let's look at a different example where we don't have a straight line. Our second example, find the average rate of change for a particle that moves according to the function f of t equals t squared over the first 3 seconds of motion. So similar to what we did before, we want to know where is the particle at the time t equals to 0 and at the time t equals to 3. When we calculate f of 0, we get 0 squared, that is 0. When we calculate f of 3, we get 3 squared equals to 9. Now the average rate of change would be 9 minus 0 divided by 3 minus 0. That would be an average rate of change of 3. Calculating the average rate of change is a fairly simple process. Now there is going to be a more difficult process when we want to look at the instantaneous rate of change. Think about the situation when you're in a car. You can know the distance from point A to point B, and you know also how long it takes you to get from point A to point B. If you put those things together, you can find the average rate of change. Now, if you at any point during your trip you look at the speedometer of the car, you can know something that is called the instantaneous rate of change. You are able to look at and know how fast you are traveling at every moment in time. So how are we going to find the instantaneous rate of change of a function such as t squared? The linear function, as we discussed in example 1, has the rate of change explicitly shown in the equation. The rate of change, even the instantaneous rate of change, would be the slope of the line. But in a function like t squared or any other function that is not linear, we cannot read the instantaneous rate of change directly from the equation, and we do need to find it. The way to find it is by taking the limit of the average rate of change. So if we express the average rate of change as the distance y2 minus y1 over x2 minus x1, then the instantaneous rate of change v is going to be the limit when x2 goes to x1 of y2 minus y1 over x2 minus x1. We are going to assess what happens to the average rate of change as the two values of x get too close to each other, almost to the point where they are the same value. So basically what we're looking at is the limit of the average rate of change when the time interval is 0. Let's look at an example. Our next example is a particle's position is given by the function f of x equals x squared plus 1. Find the instantaneous velocity at x equals to 1. So we said that the key to find the instantaneous velocity would be to find the average velocity. So let's do that. We're going to define the instantaneous velocity as y2 minus y1 divided by x2 minus x1. In this case, we're going to take y2 is going to be the function evaluated at x2, and y1 is the function evaluated at x1 over x2 minus x1. Now I'm going to make another change because I want the instantaneous velocity at x equals to 1. I'm going to say x2 is going to be equal to 1, and I'm going to substitute x1 simply with x to get a function of x. So the average velocity is f of 1 minus f of x divided by 1 minus x. The instantaneous velocity is the limit when x goes to 1, because that's where we want the instantaneous velocity, of the average velocity. So that means that what we have to calculate is the limit when x goes to 1 of f of 1 minus f of x over 1 minus x. Now f of 1, we can evaluate it. Now f of 1, we can evaluate it, is 1 squared plus 1, that's equal to 2. So we can substitute it, and we can also substitute f of x. So this is the limit when x goes to 1 of f of 1, which is 2, minus f of x. F of x is x squared plus 1 divided by 1 minus x. Now that I have my expression for the instantaneous velocity in the form of a limit, I am going to create a table of values for this function in order to find and evaluate the limit. I went ahead and filled in the table of values. Remember, we always have to take some values that are bigger than the value we're interested in. In this case, the value we're interested in is 1. So we need to take values that are bigger than 1, but very close to 1. And also values that are smaller than 1, but are very, very close to 1. When we evaluated this function in the different values, we got these results. Now, the part in green with the values of x are bigger than 1, we can see that there is a tendency that is clear to go towards minus 1. So the closer we get to 1, the closer we're getting to minus 1. And the blue part is very similar as well. As we get closer to 1, we are going to get two values that are tending towards minus 1. So we can say that the instantaneous rate of change for this function is equal to minus 1.